My dear friends, welcome back to B Spice. This is Rambala with you. In this session, we'll continue with control valve question and answer in part 2. Okay. So, hope you had watched my videos on part 1, wherein we covered the definition of, what is CV and what is cavitation, what is flashing and what is choke flow and how cavitation can be, contained, how flashing can be contained, and some other questions like, is the velocity of fluid in a control valve critical, and why do control valves have different characteristics, and of course, the definition of linear and equal percentage. All these we have seen, right? Right. So in this session, in part 2, we'll focus on the remaining questions, friends. Okay, let's move on straight away. And once again, thanks a lot for your support. Keep supporting and keep watching, friends. Yeah. So I'll just start with the difference between rangeability and turn down. Of course, the experienced professionals are aware of this, but again, this is targeted for freshers and intermediates. The word rangeability and turn down. Generally, the term rangeability is used to describe the capability of a control valve. Capability, that is the point. Capability of the control valve, meaning ratio of maximum CV of a valve to the minimum CV at which it can control. You got it, friends? Rangeability used to describe the capability of the control valve, meaning the ratio of maximum CV of the valve to the minimum CV at which it can control. Of course, it's a ratio of this, both minimum, maximum CV and the minimum CV. But the point is, rangeability refers to the capability, right? Whereas the term turn down is generally used to describe the requirements of an application, meaning ratio of CV at maximum flow condition to the CV at minimum flow condition. You got it, friends? The flow conditions, the requirements, that is the difference. So again, I repeat, rangeability refers to the capability of a control valve. Basically, ratio of maximum CV of the valve to the minimum CV at which it can control. Whereas turn down is generally used to describe the requirements of an application, meaning ratio of CV at maximum flow condition and what? CV at minimum condition. That's it, friends. Very simple, isn't it? Yeah, okay, good. So the point to note is that rangeability of the valve must be greater than the ratio of the CV of the valve when fully open to the calculated CV for the minimum conditions of the application. You got it, friends? The point to note down is the rangeability of the valve must be greater than the ratio of the CV of the valve at one fully open to the calculated CV for the minimum conditions of the application. Okay. Okay. I will also explain that in a better way in the next slide. You will understand even more. Okay. Turn down applies to the application. So that is what we mean explained earlier, right? It's a ratio of the calculated CV, okay, at maximum condition to the calculated CV at the minimum. So rangeability applies to the valve, and it's a ratio of the CV of the valve fully open to the minimum CV of the at which it can control, right? So again, I'm repeating, never mind. So the rangeability of the selected valve must exceed the turn down requirements of the application. So that is the point. So I am supporting this statement. So the rangeability of the selected valve must exceed the turn down requirements of the application. You got it? Just always remember, friends, rangeability of the selected valve must exceed the turn down requirements. Okay? Okay, I'll explain with the help of a picture. Yeah. This is what, friends? Very simple. You see here, this is the rangeability of the selected valve. You see, minimum controllable CV fully open, right? And turned on. This is what? Calculated CV at minimum, calculated CV at maximum. So this is the turn down. So this is the capacity, right? So this is the application. You got it? So rangeability must be greater than the turn down. Got it, friends? So I'm just supporting the statement here. Rangeability of the selected valve must exceed the turn down requirements. You got it? Okay, good to go. Now, can two control valves be used in parallel to handle high turn down? application. Okay. Two valves in parallel working on split range signal can give very high turn down capability. There is no doubt. Huh? Two valves in parallel working on split range can give a very high turn down capability. No worries. The situation that should be avoided, if possible, is that the larger valve operates in a cracked open position. Okay, right? So one way to avoid this is to program DCS to shut the small valve and use only the larger unit once the capacity of the small valve is exceeded. You got it? So our alternative to two valves in parallel is to select a valve which have high rangeability such as V-ported valve. Yeah, this one. You see here? This is the V-ported valve. Can you see here, friends? Yes, this is the one. So the answer is yes, but there is a situation, like larger valve operates in a crack open position. Okay, so we have to avoid this to program the DCS in such a way that to shut the small valve and use only the larger unit once the capacity of the small valve is exceeded. Okay, other alternative is to have a V-ported valve. So this is just a piece of information I want to give you. Okay, friends, very important. Okay, now what is vapor pressure? This is what I explained in part one actually. So the definition was not there. I only talked about cavitation and flashing, but here I'm going to give the explanation. Okay. The terms vapor pressure applies to a liquid and is the natural equilibrium pressure that exists inside the closed vessel containing the liquid. Very simple, friends. The term vapor pressure applies to a liquid. Okay, liquid, that's it. And is a natural equilibrium pressure. It's nothing but natural equilibrium pressure that exists inside a closed vessel. That's it, friends. So this gentleman vapor pressure varies with the temperature. That is the point. And here some explanation is there. I'm not sure whether you will follow, but I'll just read out. See, the vapor pressure of a water at ambient temperature of about 20 degrees Celsius is in the order of 4 kPa atmosphere. Absolute, yeah, 4 kPa absolute, which means that the water will boil at 25 degrees centigrade if an external pressure is reduced to an absolute pressure of 4 kPa. At 100 degrees C, the vapor pressure of water is 101 kPa absolute, right? So, which means that the water will boil at 100 degrees C at sea level, not sea level, where atmospheric pressure is about 101 kPa. This is just a piece of information I want to share. Nothing to worry. Just focus only on this. So the term vapor pressure is applies to a liquid and is a natural equilibrium pressure that exists inside a closed vessel. That's it. This varies with the temperature. Only you take this point, friends. Okay, good to go. Now, what is incipient cavitation? Incipient means it's the starting. Okay, incipient cavitation begins when the pressure first dips below the vapor pressure and continues until the flow becomes choked, at which point full cavitation is said to take place. So this is the meaning of incipient. Incipient means starting. So incipient cavitation begins when the pressure first dips below the vapor pressure and continues until the flow becomes choked, at which the full cavitation is said to take place. Okay, friends. In fact, we covered what is choke flow and all, right? I don't know whether you have watched that. So if you are not watched, you can, spare some time. Choke flow we also covered in the earlier video. Okay, basically, choke flow is a condition, wherein an increase in pressure drop across the valve no longer has any effect on the flow rate through the valve. That is the point. On one point of time, even an increase in pressure drop will not have any impact of the flow. Flow will be very constant. That's it. Okay, that's it. So now, is the flow through valve turbulent or laminar? Is flow through a valve, control valve, is a turbulent and laminar? Of course, flow through control valve is always turbulent. Laminar flow takes place with liquids operating at low Reynolds number, which occurs with liquids that are viscous and working at low velocity. Just remember, friends, flow through control valve is always turbulent. Okay, laminar flow takes place with the liquids operating at low Reynolds number, which occurs with liquids that are viscous, working at low velocity. So laminar flow in gases and vapor, very rare scenario, very seldom will be experienced in process plant. So point is, flow through control valve is always turbulent fluids. Okay. Of course, some cases laminar flow will take place, but where operating at low Reynolds number, which occurs with liquid that are viscous and working at low velocity. You got it? I hope all these are useful, right? Okay. What is one by cryogenic? Cryogenic valves operate at temperature below minus 100 degrees C, right? So these valves have an extended bonnet. As you can see here, this gentleman is extended. Okay. So to remove the stuffing box from the actuator, all this away from the source of cold, here is the pipeline, right? So everything will be cold. Okay. So to remove this stuffing box and the actuator away from the coal and are made of such as stainless steel, monel or bronze that do not brittle at this temperature. That is the point. You got it, friend? This point is very important. Monel, stainless steel. Okay. Now, what material can be used for oxygen service? Oxygen service. Okay. Monal bronze austenitic stainless steel. That's 316 or the best material for oxygen service. This is the order of preference. First choice is monal. Okay. Right. Higher the velocity, better the material to be used. So that is the thumb rule. Velocity should not exceed 40 meter per second in the valve body with monal and bronze and should be less than 20 meter per second with stainless steel. So now you can see monal can withstand up to 40 meter per second. So this is the point, friends. I hope this is also interesting, right? Oxygen service. Yes. Right. Good to go. Why do oxygen valves require degreasing? Oxygen valves. Okay. So in the presence of most oils and greases, the oxygen will burn or explode, right? In the presence of most of oils and greases, oxygen will burn or explode, right? So even oil deposited on a component, by an uncovered hand is sufficient to cause a problem, which is why, always a plastic glove should be used when building degreased valve. You got it, friends? Yes, that's the point. That is the one. So now very interesting. Why is live loading sometimes offered on valves? You see here, friends, this is the packing, right? You have this live loading. So the addition of Belleville springs, here, this guy, to the gland follower studs maintain the packing of the load of the valve. It actually maintains, actually. See, live loading reduces the need for routine maintenance. That's the point. Okay. So live loading is recommended on application where as leak along the valve shaft would likely to cause damage to the shaft and packing. That is the point. So it's recommended on application where leak along the valve shaft would likely to cause damage. Okay. Then high pressure water and steam application are example where live loading is advantageous. So you can just imagine this. High pressure water and steam application are example of where live loading is advantage. Okay, friends, got it? Yeah. Okay, good. Now, another important thing. Why is reduced trim required in a control valve? We call it as a reduced trim, right? Yes. See, this is the full port trim. As you can see here, this is the port size. See, friends, bigger, right? Yes, this is a gauge guided globe bar, port size bigger. Now you see here, see the flow comes like this and goes like this, right? You see here, this phenomena. You see here, this size, port size is less, right? Yeah, reduced port trim. This is what I'm going to explain here. Control valves are sized according to the application requirements and must satisfy both CV and velocity criteria. You got it, friends? So that is a common item. Control valves are sized according to the application requirements and must satisfy both CV and velocity criteria. This we all know, right? So reduced trim is used where it is necessary for the valve to have a CV capacity smaller than the maximum possible in that size of the valve. That is important. Reduced trim is used where it is necessary for the valve to have a CV, smaller capacity than the maximum possible in that size of the valve. Okay. To explain further, you see, the most common reason for reduced trim is that the flow rate is low for the size of the valve required. Okay, particularly where 25 mm, 1 inch valve have been specified as a smaller size to be used. Okay. Some plans stipulate that no control valve should be less than 2 sizes smaller than the line size, right? You got it, friends? We call it as one size, right? So, like for example, line size is 4 inch, then we should have a 2 inch valve, right? Right? So, that is the point. Some plans stipulate that no control valve should be less than 2 sizes smaller than the line size. Other that the valve should not be less than half the line size. Okay. So the second reason is that on the high pressure drop gas or vapor application in the valve is invariably sized on the outlet port velocity limit, and CV required is much less than the full bore CV. Okay. I don't know whether you got it. Just to, explain further. Of course, control valves are sized according to the application. That's okay. Reduced stem is used wherever it's necessary for the valve have a CV capacity smaller than the maximum possible size. You got it? Yes. So the most common reason for the reduced stem is that the flow rate is the low for the size of the flow rate is low for the size of the valve required. Particularly, if it is one inch valve. Okay. Yeah. So, because some plant, we say, right, no control valve should be less than 2 sizes, right, than the line size, right? So, and the other is that the valve should not be less than half of the line size. Should not be less than half the line size, right, friends? You got it? The valve should not be less than half the line size. Okay. Another reason is that on the high pressure drop gas or vapor application, the valve invariably sized on the outlet port velocity limit, right? So the CV required is much less than the full bore CV. So that is why we used to have this reduced port. Okay. I hope you got it, friends. Okay, good. So now, why is energy dissipation an important factor in control valve selection? Why is energy dissipation important in a control valve selection? Of course, very, very important. All control valve cause pressure drop in the fluid as it passes through the valve. Right, friends? So all control valve cause pressure drop in the fluid as it passes through the valve. This we all know, right? Since the pressure is a form of a potential energy, this means that a certain amount of energy is converted from potential energy into some other form, right? So higher the pressure drop, greater the flow rate. Got it? Then more energy will be dissipated. Okay. So depending on the type of valve and trim design, this energy can cause significant damage to the valve component due to cavitation, high velocity, or can be environmentally unfriendly because of the high noise level. Right, friends? So through careful choice of the valve type and correct trim design, it is possible to minimize the adverse effects of the high level of energy dissipation. So energy dissipation is a very important factor. So that is the point. No? This is more of a story only, friends. Just read out and try to watch 2 3 times. Then you will understand better. Anything you can write to me. I'm always there to support you. Okay, friends. Thanks a lot for your time and thanks for watching. And if you like this video, you can show your support, whatever means. Okay, by subscribing or by liking.